We're going to study now the method of Lagrange multipliers that allows us to find extrema with constraints. So what we mean by this is that we have a function that we wish to optimize, but we are not working over the full Rn, R2 or R3, or its natural domain of definition, but we restrict our attention on a much smaller set that is defined by an equation. So pretty much the standard problem that we will have to deal with will look like this. So find the minimum or the maximum or both of the function f of xy. We're going to work with two variables, even though we can have very similar problems with three variables and more conditions. Under the condition that g of xy is equal to 0. So what we're going to do is we're going to call this the objective function. So this is going to be called the objective function. And this is going to be called the constraint. Again, if we have more variables, it is conceivable that we can have more than one constraint. We will, what this method is going to give us is really critical points. And if we're lucky enough and we can guarantee that a minimum or a maximum or both exist, then we will be able to translate those critical points into extrema. So it's actually kind of interesting to see what we do in such a case. So in this case, we pretty much introduce an auxiliary variable. So, and we consider the following system. So the gradient of f is lambda times the gradient of g. This is the auxiliary variable, which is also known as the Lagrange multiplier, lambda. If we have multiple constraints, then we may have to use more such variables. This is something that we're not going to see. And then we will have one more equation that will ensure that whatever we find actually belongs to the original set. I should say here about the constraint that sometimes the constraints are going to be given through an equation, and we can always translate them into the level set of a function g with level value 0 by just moving everything in that equation to the left-hand side. We're going to see many examples of how this works. And here I should say that the first equation that I wrote in this system is actually a vector equation, so it translates to two equations. And the last one makes that three equations with three unknowns. The unknowns are going to be x, y, and lambda, but lambda is really an auxiliary unknown, and we're going to see that we're not really interested in determining its value. But sometimes we might end up determining its value as part of finding the x and y's. Now, it should be actually a little interesting to, actually very interesting to give an explanation of why this method works. And let me put it this way. So suppose that we have a function of two variables, and the constraint is a certain curve. So let's say that this is the curve defined by g equals 0. And imagine that we have a critical point for the function f on this curve. So what that would mean is that the directional derivative along all directions that are within the constraint, which means they're tangent to this curve at the point under question, give are zero. All the directional derivatives in those directions are zero, which means since the directional derivative is the gradient at the given point, so let's say that this is the point AB, so the gradient at AB times those directions that are parallel to this curve should be equal to zero, which means that this vector should be perpendicular to all directions that are parallel to the curve at the point AB. Yes, but we do know a vector which is perpendicular to those directions too. What is that vector? It's the vector of the function that defines that curve as a level curve of it, and that would be the gradient of G. So basically what we're going to have is that these two vectors should be parallel to each other. And hence, that's why we're saying that the gradient of F should be equal to lambda times the gradient of G at every critical point. It's not important to know this explanation and in order to solve problems, but I had to make this parenthesis here because it's rather quite interesting why this rule can be used and how this can be interpreted pretty much on the principle of what the directional derivative is and the fact that the gradient is of a function that defines a level curve is perpendicular to that level curve. So here's what I would like to do. I would like to actually work with the same constraint. It's going to be pretty much an ellipse and vary the objective function in order to show different ways of solving such systems. It should be pretty straightforward to write down these systems, but once we try to solve them, we may come up with interesting situations. So I would like to give several examples of the constraint being an ellipse. An ellipse is a compact set, which means that the existence of extrema is guaranteed, which means I will be able to work with a table of values on each case, and then find the minimum and the maximum of the objective function for different types of objective functions. So let's begin with our first example. So we're going to see for the first time how this method works. So find the minimum, I should say, find the minimum and the maximum of the function f of xy equals to x plus 3y on the ellipse x squared plus 3y squared is equal to 9. Okay, let's see how we do this. So first of all, the first order of business is to write the ellipse as the level set of a function of two variables. So that's why we bring everything to the left-hand side. And we say define g of xy to be equal to x squared plus 3y squared minus 9. So that function would give us the set on which we're interested as a level set with level value 0. So the system that the method of Lagrange multipliers stipulates is that the gradient of f should be lambda times the gradient of g, and g should be equal to 0. And this translates to what? We will have the gradient of f is 1, 3. That should be equal to lambda times the gradient of g, which is 2x, 6y. And also, we should make sure that x squared plus 3y squared minus 9 is equal to 0. Let's write it as equal to 9. It's pretty much the same thing. And this translates to 1 is equal to 2 lambda x, and 3 is equal to 2 lambda, 6 lambda, actually. Um, 6 lambda y. And eventually x squared plus 3y squared is equal to 9. So how can we solve this system? So in general, nonlinear systems do not have general methods, but what I would like us to do is look very carefully at the solution of these systems as we give them, and pretty much mimic what we do here, or get some ideas about how such systems can be solved. So for the first one, let's notice that the first equation implies that lambda cannot be 0 and x cannot be 0, because if any one of them were 0, then the product 2 lambda x from the first equation on the right-hand side could never be equal to 1. And y cannot be equal to 0. So what we can do is take the first two equations and divide them by parts. So we will have 1/3 is equal to 2 lambda x over 6 lambda y. And we cancel the lambdas. And also we cancel the 1/3. So we have that 1/3 is equal to 1/3 times x over y. And these two things cancel, and eventually we get 1 is equal to x over y, which means that x is equal to y. Okay, once we know that x is equal to y, then we can plug it into the constraint, and that will give us y squared plus 3y squared is equal to 9, which means that y squared is equal to 4 over 9. Actually, it's not 4 over 9, it's 9 over 4. Sorry about this. And y is equal to plus or minus 3 over 2. And of course, since x is equal to y, the 2 points that we get are 3 over 2, 3 over 2, and negative 3 over 2, negative 3 over 2. So we put them in a table. In many cases, it's advisable to come up with a table right away. So what we found are critical points, but since the constraint represents a compact set, it's the ellipse, it's bounded, and certainly it is its own boundary, then we can just plug them into our function and see what happens. So we're going to get 3 over 2 plus 9 over 2, that will be 12 over 2, also known as 6, and here we will get negative 6. So this will be the maximum, and this will be the minimum. And actually, here, sometimes there is a good question of whether when we give the minimum and the maximum, should we give the inputs, should we give the outputs? Here we give both, and that works just fine. Okay, so now let's solve another problem. So here's another example. So find the minimum and the maximum of f of xy is equal to x times y this time. So let's take x times y. On the ellipse, let's change it a little. X squared plus 2y squared is equal to 4. Okay. And as I said before, since it is guaranteed that a minimum and a maximum will be on this ellipse, will exist on this ellipse, we can start. The very first thing that we could do for all of these problems is actually start a table. And as we find the critical points, just put them on the table, eventually evaluate the function. The largest output will point us to the maximum. The smallest output will point us to the minimum. So again, we have to start with a constraint and bring everything to the left-hand side, and then define g of xy to be x squared plus 2y squared minus 4. And the system is, again, the gradient of f is lambda times the gradient of g, and g should be equal to 0. And this translates to, let's go directly to the partial derivatives this time. So the partial derivative of f with respect to x is y is equal to lambda times the partial derivative of g with respect to x, which is 2x. And the partial derivative of f with respect to y is x equals to lambda times the partial derivative of g with respect to y, which is 4y, and x squared plus 2y squared is equal to 4. So how do we solve this one? Actually, this one is solved with a similar consideration. So note that x cannot be 0. Why? If x goes equal to 0, then the first equation would imply that y is equal to 0, and that's impossible because of the constraint. Because of x squared plus 2y squared is equal to 4. So y cannot be 0. I'm sorry, x cannot be 0. For exactly the same reason, y cannot be 0. So if y were equal to 0, then the second equation would imply that x is equal to 0. And again, that's impossible because of the constraint. And finally, lambda cannot be 0. Because of the, again, because of the constraint. I'm sorry, because if lambda were 0, then both x and y would be 0. So if for example, lambda was equal to 0, then that would imply that x is 0 and y equals 0 because of the first and the second equation, which again is impossible because of the constraint. So what does that mean? That means that x is not 0, y is not 0, and lambda is not 0. So we can do something very similar to what we did before, which is divide by parts. So the first two equations, y over x, lambda is equal, lambda times 2x, lambda times 4y. And this will give us, so the lambdas cancel each other. We cross multiply, and that gives us 4y squared is equal to 2x squared, which means that x squared is equal to 2y squared. And now, every time we get something like that, we go to our constraint and we plug it in. We replace x squared by 2y squared, and that gives us 2y squared plus 2y squared is equal to 4. Which means that 4y squared is equal to 4, which means that y squared is equal to 1, which means that y is equal to plus or minus 1, right? So now, if y is 1, then the very first equation means that 2x squared will be equal to 4, which means that x squared will be 2, which means that x is equal to plus or minus square root of 2. So this gives us already 2 points. What are they? Square root of 2, 1, I put it on my table. And negative square root of 2, 1, I put that on my table too. If y is equal to negative 1, then what do we get? We get that, again, the same story pretty much. 2x squared is equal to 4, x squared is equal to 2, and x is equal to plus or minus square root of 2. So this time around, we have 4 points to deal with. And if we plug them into our function, it's actually quite straightforward to find what we have, what we get here. So we will get what? We will get square root of 2 here, negative square root of 2 here, negative square root of 2 here, and square root of 2 here. So this gives us a maximum. This gives us another maximum here. This gives us a minimum, or the minimum, if you like, and this gives us the other minimum. So the maximum for this function occurs at 2 points, and the minimum also occurs at 2 points. So let's do another example. Now, again, let's vary a little the objective function. So find the minimum and the maximum let's do a couple of squares now on the objective function of f of xy is equal to x squared minus y squared on the ellipse. Let's go back to the first one, x squared plus 3y squared is equal to 9. So how do we do this one? Again, let's start with our table. The reason we do the table is because of the fact that the constraint defines a compact set on which extrema are guaranteed to exist. So this means that we will have, let's start by making up the function that will give us the constraint. So by now we should already know that we make up that function by bringing everything to the left-hand side. So that should be enough here. The system is that the gradient of f is a scalar multiple of the gradient of g with this coefficient lambda, and g should be equal to 0. And now again, we should be able to write the equations directly. The derivative of f with respect to x is 2x, and that should be equal to lambda times 2x, which is the derivative of g with respect to x. The derivative of f with respect to y is minus 2y, and that should be equal to lambda times 6y, which is the derivative of g with respect to y. And finally, x squared plus 3y squared should be equal to 9. Okay, and this will give us what? Now, here we're going to do it a little differently. So we will start with the first equation, and we bring everything to the left-hand side. So we have 1 minus lambda. We could factorize it right away, but let's show it in detail. 2x minus 2 lambda x is equal to 0. We get that from the first equation. And now if we factor out x and 2, if you like, we get 1 minus lambda is equal to 0. So this gives us two possibilities. The two possibilities are that x is 0 or lambda is equal to 1. Let's explore each one separately. So if x is equal to 0, then because of the constraint, that will give us 3y squared is equal to 9, right? We plug it into constraint and it gives us that, which means that y squared is equal to 3, which means that y is equal to plus or minus square root of 3. So that gives us 2 points here. So that gives us 0, comma square root of 3, and 0, comma minus square root of 3. And the second possibility, as we said, is that lambda is equal to 1. So what do we do if lambda is equal to 1? If lambda is equal to 1, then we plug it into the second equation, and that gives us that minus 2y is equal to 6y. Yeah, but how can you possibly have that? Bring everything to the left-hand side, to the right-hand side, and that will give you 0 is equal to 8y, which means that y is 0. And now it's the same game. once you know that y is 0, then you plug it into the constraint, and that gives you x squared is equal to 9, which means that x is equal to plus or minus 3. And that gives you 2 more points, 3, 0, and negative 3, 0. So we plug in we plug them into our function, into our objective function, and what do we get? We get minus 3 here, and then 9 and 9. So this is the minimum, and it's also here. The minimum is also here. This is the maximum, and this is the maximum. Okay. And why don't we solve one more? And now let's play with one quadratic and one linear term. So let's have something like, so here's our example. Find the minimum and the maximum of f of x, y is equal to x plus 2y under the constraint. So I could have said on the ellipse, but that's the same thing. X squared plus 2y squared is equal to 4. Okay, so again, first order of business here, start your table. This is a compact set. Sometimes, even if it's not a compact set, you can actually get the table going anyway if you have some other reason to explain why the constraint, why the minimum and the maximum could exist. So for example, you have cases where the objective function is obtained through a distance problem, a minimum distance problem. And in those cases, you can explain why the minimum should exist and then find the critical points through the method of Lagrange multipliers, and again use a table, even if you didn't have a constraint that led you to a compact set. So in any case, let's define the constraint function. I hope the examples we have seen so far are leading us easily in doing so. So it's x squared plus 2y squared minus 4. And we will have that the system is the gradient of f is lambda times the gradient of g, and g should be equal to 0. And okay, so let's see what the derivative. Oops, I said 1. So I will have to make one of them quadratic. So let's make it x plus 2y squared. So I just changed the function so as to get the one quadratic term. So let's see what we get here. So we will get x. So it will be the partial derivative of f with respect to x is 1 equals to lambda times 2x. That's the partial derivative of g with respect to x. And then the partial derivative of f with respect to y is 4y. And that will be equal to lambda times the partial derivative with respect to y of g, which is 4y. And then, of course, the constraint is the last equation for this system. And how do we solve this one now? Well, the starting point in this case is the second equation. So we start with the second equation. And we bring everything to the left-hand side. And we factorize 4y. So this will be 4y times 1 minus lambda is equal to 0. Again, this has two possibilities. Y is equal to 0 or lambda is equal to 1. If y is equal to 0, then we plug it directly into the constraint, and that gives us x squared is equal to 4, which means that x is equal to plus or minus 2, and that yields 2 points, 2, 0, negative 2, 0. On the other hand, if lambda is equal to 1, we plug it into the first equation, which gives us that x is equal to 1/2. And if x is equal to 1/2, and we know that, then we plug it into our constraint, which gives us 1/4 plus 2y squared is equal to 4. which will imply that 2y squared is equal to 4 minus 1/4. So that's 16 over 4 minus 1/4. So that's 15 over 4. And eventually, we will get that y squared is equal to 15 over 8, which means that y is equal to plus or minus square root of 15 over 8. I mean, you can slightly simplify this as a square root of 15 over 2 square root of 2, but I'm not sure there's such a need, so allow me to keep it this way. And we have 2 points. The points are going to be 1/2 and square root of 15 over 8 and 1/2 and negative square root of 15 over 8. And now we can plug them into our function. So if we plug in 2, 0 into our function, we get 2. If we plug in negative 2, 0, we get negative 2. And if we plug in the last 2 points, actually, we will get the same thing, which is how much? It will be 1/2 plus 2 times 15 over 8, which is the same thing as 1/2 plus 15 over 4. So that's 2 over 4 plus 15 over 4. That will be 17 over 4. So 17 over 4 here and 17 over 4 there. Which one is largest? Between 2 and 17 over 4, of course, it's 17 over 4. So that's the maximum. That's the maximum. And that's the minimum. And in this case, the point 2, 0 is neither, actually. It's neither a minimum nor a maximum. It could be a local minimum or a local maximum, but again, there is no need for us to go any further because from the very beginning, we were looking for global extrema in this problem. And so this point becomes irrelevant. So we saw how the different methods varied as we varied the objective function. And this game can be played in all sorts of different ways. And this was just a sample of some techniques. In general, the systems that one can get from the method of Lagrange multipliers can be quite complex. But you saw some examples of how one can play with them and get the critical points. And that's all. Thanks for watching.